Swayam Prabha. Digital India. Educated India.
Let's now see how the hidden layer values are computed. In this case, the network is fully connected. The input to the network is a one-hot vector, as I mentioned earlier. Again, W is the weights on the input hidden layer side, and then W dash is the weights on the hidden layer to the output layer side. When we compute the hidden values in the hidden layer, we use a dot product to get that, right. So, this is represented in the vector form right now. So, the bold letters we have the vector representation. As I mentioned earlier in the earlier session, use a linear algebra package so that you can directly compute this instead of going through the loop method. Okay. So, in this case what happens is you have the hot vector like this, and then you have the weight vector, and what you want to find is your h, right. So, let us say this is phi by 1, and then we want to have the weight vector which is of size, we want to have the hidden layer of size, let us first define that as 3 by 1. Then what is going to happen is this is going to be a 5 by 3 matrix, right. So, what you do is you just do the W transpose into X, that is 3 by 5 into 5 by 1 will give you 3 by 1 here. Okay. So, when you do this operation, what happens is it actually copies the row in the weight vector and then places them here. Okay. Since all the values are here, so it does not matter whatever value that you have in the weight, it only takes the row corresponding to the value of 1 in the one hot vector and copies that particular row into the hidden layer. Okay. So, now what we are going to do is we are going to be creating some more representations. Okay. So, we have done the calculation of h using this model. So, now we have the other side from the hidden layer to the output. So, we apply the similar mechanism to compute uj. Uj is equal to the VWJ dash transport and h. So, you remember there is a hidden layer, and then there is a output layer, and then we have another weights matrix, right. So, this is computed. So, we want to do the dot product of these two and then create the output layer, right, and this is what is shown here. The uj is computed by taking these values and then using the wij, and we get the output values as uj, and the size of this would be equal to 5 by 1. Okay. So, you are clear with this? So, we have computed first the hidden values, and then from the hidden values to the output, again we have a matrix here. So, we have computed this, and then using this we are going to be computing another set here, right. So, let me use one more layer to clearly explain what happens. So, in this output layer the values are computed and then later we apply the softmax to get these values, okay. And this is what is shown in this equation. Okay. So, that output values are computed before applying the softmax and uj represent that output values. Okay. So, in this case VWI is the vector representation of the input word that we have provided as the one hot vector, and then V dash Wj is the jth column of the W. So, in this case your jth column. So, you have this matrix here and then we are taking the jth column of the, okay. And then later what you do is, as I mentioned earlier, in the output layer we are going to be applying the softmax. That is where we are going to get the real values of the predicted word, correct. So, the real value would be computed using this approach, uj equal to exponential of uj divided by the sum of the j dash equal to 1 to v exponential of uj dash, this uj dash, not this. Okay. So, do not get confused with the index values. We will be using j, j dash and j star. Okay. So, these are all these indexes that I will be using and each one would be having the value from 1 to v, just to distinguish between the input, the output and the predicted elements. We will be using 3 different indexes here. Okay. So, we are going to be predicting the value of yj using this model. So, in this case we are going to get one vector of size v, okay. And then we want to find out what is the actual error or what is the actual value predicted, and then if the actual value predicted is same as what is input, then there is nothing much we can do, the system has learnt it. If there is a difference, we will take the error and then do the back propagation algorithm. Okay. So, it is very similar to what we had seen earlier. Again I am going to repeat this one more time. So, we will compute the values in the hidden layer using this formula, right, and this is nothing but just the copy of one of the rows corresponding to the input one hot vector, and then from the hidden layer to the output layer we have w dash ij. Using that value we are going to be computing the output values, and uj is our output value, okay. And then each column of the wij is used for the computation of this uj values, okay. Okay. And then later in the output layer we apply the softmax, so that the probability is distributed across the vocabulary set. All right. So, the next question is, how do we really update the weights? So, this is very similar to what we had seen in the back propagation model. There is no change in the way we are operating right now. The only change that we are going to be introducing is bring in a different error mechanism, okay, or bring in a different model for the error and use it for making the corrections in the weights as we move along, right. So, we have the value that is computed. Supposing if this is the target and we have yj, I want to make sure that this value is minimized, okay. So, using yj we are going to be minimizing the error, and then back propagate that error into the weights and then keep repeating that until it becomes very close to 0 or certain condition that we have defined. Okay. So, in this case, as I mentioned earlier, there is an separate index created for the softmax layer as well, that is called J star. Okay. Y J star minus T is going to be our error value. So, we want to be able to minimize that error, right. So, minimizing the error is same as maximizing the probability of that predicted word. So, we are going to be using a different scale here in terms of the errors. We are going to be using loss function, which is called as the cross entropy measurement. So, why do you want to use this mechanism? So, if we look at the log px or the predicted value that we have here, it is very well scaled. Okay. Selecting the step size to move forward in terms of the error correction is easier in this. And then when we introduce the probability and then when you start multiplying them, the values become smaller and smaller as we progress, and sometimes it leads into the underflow. So, instead of multiplication, now we try to get into the log framework where the multiplication becomes addition, right. So, that is the reason why we want to have this. The one more advantage also, it provides a good measure of error distance. For example, if the value becomes 1, okay, so the error value would be, which would be equal to 0. Okay. So, we normally do it y into this. So, if this is, if there is an error value which is not equal to 1, which is smaller than 1, this value will be larger. So, it gives us a good visual feeling with respect to how the error is getting reduced. So, that is the reason why also we use the cross entropy measurement for error reduction. So, we can also see that it is a very special case of cross entropy measurement between two probability distributions here. Okay. All right. So, how do we now update the weights? So, we update the weights using the partial derivative that we have seen. So, we know that the error in the predicted value is given by yi minus tj, which is equal to ej, and this is what we want to minimize, correct. So, ej is our prediction error. So, we want to be able to find out with respect to the wij that we find between the output and the hidden layer, right. So, when we want to do that, we use the chain rule, which goes like this: dou e by dou uj into dou uj by dou wij dash, which is nothing but we know that this is ej, and when you do the differentiation with respect to wij dash, this is hi. Okay. So, the dou e by dou wij dash is ei hi. So, this is one thing that we have found. So, now we want to update the weights. How do we update the weights? So, now we have some learning parameter, as we had mentioned earlier in the previous back propagation network. In the same case, we will have a learning parameter and we will have the value between 0, 1 to some, depending on the network weights and all that. Okay. So, in this case, we are going to be computing the new weights using our old values. Okay. So, once this is computed, now we have a new set of matrix in the hidden to the output layer, correct. So, based on the error reduction mechanism, the values have changed. All right. So, in the same fashion we should be able to reduce the weights between the input and the hidden weight. So, we have moved from the error from the output layer to the softmax layer and then propagated the error back to the weights, and now the weight vectors are changed. From the changed weight vectors, now we have to move that back into the input to the hidden layer, so that the values there in the input to the hidden layer weights are also changed. Okay. So, again taking the derivative with respect to hi, we get the value of ehi. We are going to be taking the derivative with respect to wki, which is nothing but the input to the hidden layer weights, right. So, that we are going to be changing. For us to change that weight, so we need to differentiate that or do the partial differentiation with respect to wki, and we have the error and we have to change it with respect to this, right, using the rules, chain rule. Again we will rewrite this equation in this fashion and then find the values that we want to use to update the input weights. Okay. So, since this is known, and then if you do the partial differentiation with respect to wk, what you will get is the input value, right, and then the weights are updated using the old values and the error that we have computed, which will be multiplied by the learning parameter in this case. Okay. Is this clear? All right. So, let us move on to the next one. So, these are some of the insights that you will have. The prediction error propagate the weighted sum of all words in the vocabulary to every output vector, right. The change in the input vector is defined by the output vector, which in turn is updated due to the prediction error, correct. The model parameters accumulate the change until the system reaches a state of equilibrium. That means, the model parameters are those which are computed using the error propagation, and finally, when there is no more change that can be accommodated, we freeze that. That is when the model parameters are created and ready for testing our model. This particular bullet point is meant for the same word learning, in terms of learning the same vocabulary words and then creating the word vector form, but in our case this is not true. The rows in the input hidden layer store the features of the words in the vocabulary. Okay. So, once the training is completed, what we have is the embedding of that particular vocabulary that we try to learn. Okay. So, let us now look at some of the operations that we had seen earlier in terms of the matrix form. So, what I am going to be doing is I am going to be really drawing those matrices, so that whatever equation that we had seen and whatever error propagation that we try to define using the equation will become very clear. Okay. So, what we let us take one small example. Actually, I have notes taken for this, so that I do not make any mistakes while repeating this. So, I am going to be copying those values from the notes here. Let us say we have the words that we want to train. Okay. So, this is the sentence that I want to train, and then if you want to look at the corresponding one hot vector, let us say we are going to be taking this word, it is going to be like this. correct. So, this is going to be our one hot vector corresponding to V. So, this is of size 6 by 1, and then let us say that we are going to be constructing a matrix of size 6 by 10. So, this is just an example. So, I am just taking a matrix of size. So, this is our W K I in the earlier case, remember. So, if you look at this, we will have about, I am going to draw only one row here. Okay. So, we have 6 rows in this. So, corresponding row will be just copied as I mentioned earlier into H. Okay. So, when we do the linear combination of this, this would be copied into this. So, this would be 10 by 1. So, how do you obtain this? You take a transpose of this and then do a dot product with this input value and you get this 10 by 1 matrix. Okay. So, this is our input to right. So, what is the next step? Using this we use another to create our output, correct. So, we use this, the matrix size is the same, is 10 by 6. Okay. So, we have 10 elements in this and then doing a dot product of this would give you the output. See, the size of the output would be very same as the input, which will be equal to 1. Okay. So, in this case, since we are using a bag of words, for the input word V, this network should learn log, right. So, we have some values, 6 values are computed, and then for this we take a softmax. Okay. And then the softmax will do the probability distribution between 0 and 1 for all the values, and we need to find the corresponding context word, right. Okay. So, let us see how that happens. So, in this case, okay, let me draw the softmax here. So, after this we compute the softmax again of the same size 6 by 1. Okay. So, we have computed the softmax for this, and this softmax will again give you 6 values. So, let us assume that this value is what we want to predict, right. So, it would have given values for each of this. Since the initial values of the weights are random, we cannot expect this word to have the maximum value. So, it will have some random values because of the weights that we have created in these two cases. Okay. So, now once this is computed, we want to find out the error between the predicted value and the target value.